Hi everyone, I'm June. Thanks for coming to my talk today for our work SUBPLEX, a visual analytics approach to understand local model explanations at the subpopulation level. Local explanation techniques are popular to interpret a machine learning model's behavior on a single instance. For example, here shape values indicate how the model output is attributed to different feature values. However, local explanations do not scale to the understanding of model behaviors on the whole dataset. To understand the patterns of a large set of local explanations, it is natural to conduct subpopulation level analysis. For example, we can apply clustering and projection techniques. However, it is possible that we cannot see any significant group structure in the data due to high dimensionality and the sparsity of the local explanations. To overcome this issue, we are motivated to introduce human input to refine the results of the computed subpopulations. For example, a domain expert knows that pro-line is more important when the model makes decisions. They want the clustering and projection to rely more on this feature. After the refinement, we can see more clear subpopulation structure in the example visualization. So here comes the questions. How do we introduce human input to clustering and projection? How do people know which feature is more important? And what else should we do to better support local explanation analysis? To answer these questions, we introduce SUBPLEX, a Jupyter Notebook widget which is supported by the human-in-the-loop pipeline of feature recommendation, subpopulation customization, and subpopulation interpretation. In the rest of the presentation, I will first introduce the design process of SUBPLEX, a steerable subpopulation analysis methods, the actual tool of SUBPLEX, as well as evaluation of this tool. To support the local explanation analysis, our goal is to help data scientists understand model logic through local model explanations. Specifically, we want to assist them to answer how do different features influence the model predictions. As such, we first conducted hierarchical task analysis. This is a really common and useful method in HCI domain, with the goal of understanding how do different features influence model predictions. Data scientists first group the instances with similar local explanations. Then they inspect the characteristics of each group. Next, they want to make sense of the patterns. After a few iterations, in the end, they export the patterns for further analysis. During hierarchical task analysis, we further decompose each task. For example, to make sense of local explanation patterns, a data scientist wants to explain the pattern differences from different subpopulations. Based on this, we then extract an abstract task of pattern comparison, which lead to one of the design requirements of visual comparison of local explanations. In the end of hierarchical task analysis, we identified 5 design requirements, including feature selection for clustering refinement, support to user-defined subpopulations, pattern identification, visual comparison of patterns, as well as support to coding environment, such as a Jupyter Notebook. To reach these requirements, we need to first support steerable subpopulation analysis, that is, to introduce human input into clustering and projection. Let's first give a formal definition to a local explanation. In this work, we assume a local explanation is a vector, where each dimension represents the attribution of a feature Wi to the specific model output. And to steer the subpopulation analysis by humans, our goal is to make the clustering and projection of local explanations depend more on human-specified features. Since humans prefer different clustering and projection techniques, to generalize our steerable techniques, we focus on distance adjustment. For example, we have Euclidean distance calculated in this way, where we apply alpha to user-specified important features and beta to the rest of the features. By default, alpha equals to 0.9 and beta equals to 0.1. So this is how we refine the subpopulations as we described in the beginning of this talk. Besides prior knowledge, how do we know what features might be more important? So we identified three properties to score the features. First, consistency, which is the variance of feature within each cluster. Next, separation, which is the difference of the feature values across clusters. Lastly, importance, which is the significance of this feature in one or more clusters. Then we normalize each property within the range of 0 to 1 and then sum them up as the final feature score. In the tool we will present later, we will suggest the users to add the top 6 features with the highest feature scores. Based on the task analysis and the techniques we described, we designed SUBPLEX, a Jupyter Notebook widget, to assist data scientists to analyze local explanations over the whole dataset. Here is a demo of how it provides support to a loan application model. On the left of the widget is feature suggestion view and a projection of all the local explanation vectors. On the right-hand side, it presents the local explanation distribution. The initial result of the automatically generated clusters seem okay, but the 3 clusters are somehow mixed and not separated enough. So we take the suggestions of adding the 3 features average months in file, unpaid balance, and months since lost delinquency. And then we look through the ranked features and add other important features like satisfactory trades and bills paid on time. Then we regenerate the clusters. Now the clusters seem more separated and make sense to me. By looking at the table, I find months since lost delinquency is similarly important for the 3 clusters. Unpaid balance has a really strong influence in group 2, but is less strong for the other 2. Also, average months in file has really strong influence in group 1, but much less strong in group 2 or 3. Now I've tried to figure out why they are different. Why average months in file has stronger influence in group 1? Does it make sense? I first checked the value distribution of average months in file for the 3 groups. For the first group, the values are between 0 to 400, and there are 2 peaks around 50 and 120. But group 2 and group 3 have the values mostly between 50 and 120. So I have a hypothesis that the feature average months in file has stronger influence when the average months in file has extreme values, such as fewer than 50 or more than 120. To test it, I plot the local explanation values for the instances which have really low or high average months in file, and another group with middle values. This is the local explanation score distribution for the extreme values of average months in file. Then for the instance with middle values, the influence is usually less strong. To evaluate SUBPLEX, we collected feedbacks from 8 data scientists from financial domain. All the participants agreed that this widget is useful for them to understand model behavior on the whole dataset. And compared with other tools they were using, they liked the interactivity of SUBPLEX, as well as the global view of data it can provide. We also got some suggestions for future development. Another interesting finding during the evaluation is that, although from the same domain of finance, these data scientists did have different interests of subpopulations to explore, which highlighted the importance of enabling human in the loop. We also see some limitations of this work. First, it was designed with experts from the finance domain, and did not include all types of local explanations. As for the evaluation, interviewing only 8 experts may make us overgeneralize our results. Thanks for your listening. Please read our paper for more details.